Cool. Time to go? Can we start? Is that too loud? All right. Welcome back, or welcome to our 2 o'clock Design Automation Conference panel, Trust and Verify, overcoming costly and piecemeal approaches to pre-silicon side channel attack vulnerability analysis and verification. I'm Brian Fuller, Editor-in-Chief at ARM, and we're going to talk today about one of the most serious issues that the industry's faced in the last few years. You may recall 2017, when Spectre and Meltdown came to the fore, to major league side channel attacks. The industry responded in pretty quick order. However, this still remains a challenge for security experts. And we have 4 of them here today who are going to talk us through that, explain what side channel attacks and fault injection attacks are, what some of the challenges are in protecting vulnerable systems, and how we might actually monetize this up and down the food chain in electronics design. So let me introduce our panel from your left to your right. Nearest to me is Will Ruby. He's the COO of FortifyIQ, a company that offers pre-silicon evaluation tool set built to test hardware designs against differential power analysis and fault injection attacks, and by providing side channel attack resistant IP cores. Before joining FortifyIQ, Will held leadership roles at Cadence, Sequence Design, Siemens, and Golden Gate Technology, among other companies. He has a BS in Physics from Berkeley, an MSEE from USC, sorry about that, and an MBA from San Jose State. Next up is Mike Borza. Mike is Synopsys scientist, working broadly on security and integrated circuits and systems. He has more than 25 years of leadership experience and technology experience in security and safety critical systems. In 2002, he founded and was CTO of Elliptic Technologies, acquired by Synopsys in 2015. His previous experience includes Chrysalis ITS, now Thales, Ankari, HID Global, and Alcatel Transport Automation, which is now Thales Transport. He holds more than 20 US patents and has been an active contributor to the security task force of IEEE 802.1 and was editor of the 802.1 AR Security Device Identifier Standard. Next up, we have Prabhat Misra. He is a UF Research Foundation professor at the University of Florida. He's an IEEE fellow, and he's an ACM distinguished scientist. His research interests include embedded and cyber-physical systems, hardware security and trust, computer architecture, energy-aware computing, formal verification, system-on-chip validation, machine learning, and quantum computing. And somehow he manages to get a few hours of sleep every night with that brief. He received his PhD in computer science from the University of California at Irvine. Prior to joining the University of Florida, he spent several years in various companies, including Intel, Motorola, Sasken, Synopsys, and TI. Last but certainly not least, Tom as he is known, Tom Katsiolas, is board chair, Trusted IoT Ecosystems Security with the Global Semiconductor Alliance, and head of trust chain business with Siemens Digital Industries Software. Prior to his current role, Tom was CEO of Runtime and held leadership roles with Forte, Archon Design Solutions, Amacor Technology, and other companies. He has a bachelor's in engineering from the University of Bridgeport and an MSEE from UMass Amherst. So, welcome, gentlemen. We're going to dive right in, and we're going to run through a series of slides that are going to explain side channel attacks for those of you who aren't particularly versed in these. And as I mentioned in the tee-up earlier, just because the industry responded in 2017 and early 2018 to that initial Meltdown and Spectre situation, we still have some very serious threats, clear and present danger. Now feel free, gentlemen, as we go through this, since you're the experts, if you want to comment on any of these, particularly explaining how cyber criminals make this work for themselves.
You take
Anybody
that?
want to tackle that?
Well, just as a quick introduction, what you see here on the left side of the screen is a kind of high-level picture of what a side channel attack looks like. And fundamentally, a side channel attack is a non-invasive type of an attack where a bad actor, as the industry calls it, a hacker, in other words, can measure various parameters without actually affecting the operation of the device and measure things like power traces and electromagnetic emissions. And based on the analysis, for example, of the power trace data, determine the value of the secret key in the design. And I always like likening it to somebody who reads your utilities meter and then finds the code to your alarm system of the house.
Yeah.
So that's an analogy if you want to keep that in mind. On the other hand, you have on the right side of the slide, you have the fault injection attack, which is a more invasive type of an attack. This is where you would actually inject the faults into the design, observe the behavior due to those faults, compare that with the proper behavior of the device, and again, based on the analysis of these behaviors and the differences in these behaviors, then determine again the value of the secret key of the design. So that's the two fundamental types of attacks, side channel fault injections, and within each category there are different kinds of attacks as well. So there's a suite of them.
And in some of these cases, you cannot necessarily see any evidence of an attack. Is that correct?
Well, especially with the side channel attack, which is, as I said, non-invasive. So by measuring, for example, power traces, you're not really affecting the operation of the device at all. So it is kind of like a silent but deadly type of an attack. Absolutely.
Absolutely. Okay, what do we have here?
Okay, so this is a couple of slides that we put together just again to show that it is actually pretty straightforward to hack into or attack a non-protected device, and this is a smart card example where the smart card uses a pin, and then here is we have just a simple code that looks at the pin that is being provided to the device, and then compares to the actual value, the secret value of the pin. So if you look at the power consumption trace, there's nothing really special is really going on. The key, obviously, or the pin in this case, is rejected. But again, the power trace is, basically it's a similar power signature in all the portions of the waveform that you see there. Okay. So then when you attempt to break into the device, you may guess, let's say, a value of the first digit of the pin. And what you see is now you see a higher level of power consumption. You see a spike that essentially correlates to the fact that the device is going through at least one iteration of this loop where it's checking for the proper digit. So that's just one digit when the first attempt to guess the value of the secret pin and secret key in this case. And then if you start providing more and more correct bits of the pin, you now see more higher spikes in the power consumption profile. Okay. So this example was a pretty simple Arduino-based board. It's not protected in any way, so it's not secure. And this particular video that's actually available on YouTube for you to watch goes kind of through the steps that they take to essentially hack into this device and determine the value of the secret key in the algorithm. Okay, so essentially what you're doing is kind of doing something very similar to what the bad actor or hacker would do. Measure stimulate the device, through your PC, then measure the power consumption traces with an oscilloscope. So it's a pretty simple setup. Okay. So again, you see then the captured power traces from the oscilloscope as the device is running. Okay. So what are we looking at here is we're looking at an AES algorithm, which is several rounds of operations. They take several numbers of clock cycles. And essentially, the input then is encrypted through this particular algorithm and then gets output from the device. Okay. So if you look at the power consumption trace, in this case, the peaks correspond to these rounds in the algorithm, the mathematical operations. With the correct key, you now see the peaks that are corresponding to these AES round operations. Okay. So the idea here is that you can, the key is 256 bytes, but you can look at each byte separately, and then you can essentially try to guess what the value of the key is, for a particular byte, and then look at the correlation that you observe in the power traces. What this particular demo was using is actually an open source software called JLSCA, and it actually performs the analysis on the captured traces to determine the value of the key. So that the process is very well automated. Okay, so you see here that these are the power traces that have been acquired through the operation of the device. This is essentially showing that as you are collecting more and more traces, you get higher and higher correlation score against the value of the secret key that you're trying to guess. So if your value is correct, you get higher and higher correlations in the power signatures as the number of traces is increasing. Okay, so to make this presentation short, the actual analysis time of this was less than 2 hours. So to actually set everything up, to measure the traces, run the analysis through the software, everything took less than 2 hours in real time. Okay.
Thanks, Will.
Yeah.
So I want to open it up to the panel, and then I'll open it up to the audience if you have questions, so take good notes. How widespread is this problem today, and what are some use cases that might be particularly vulnerable?
Well, the smart card and SIM use case used to be a very common one, and so that part of the market realized early on that they were targets. And they're targets for a couple of reasons. They're small devices. They do a fair bit of cryptography, public key cryptography and secret key cryptography as well. And because there isn't much else going on in there except cryptography, that makes them an ideal candidate for a power analysis side channel attack. And so those were, the kind of the leading case. They're very compact, they're cheap, they sell them for 10 cents, 20 cents, maybe up to $1 per card. And so an attacker or an adversary or bad actor, as we're calling them here, has the opportunity to get a lot of these things and start to analyze them and really start putting together what they're doing, look at the differences in how they perform over time. So that's been, a very early market that needed to respond to this, and they did. And so the smart card and SIM chip manufacturers, which are largely the same companies, knew that they were coming under these kinds of physical attacks on individual devices, and they've put in very good mitigations for power analysis side channels. What hasn't happened is that hasn't really caught on a lot of other places in the industry. So there are some very high security devices that go to a lot of trouble to mitigate these side channels, and then a lot of other devices that don't go to any trouble to try to mitigate them at all. They just assume it's such an esoteric attack that it's not realistic that they're going to come under attack. What's happening right now, and particularly in the last couple of years, is that you're starting to see artificial intelligence and machine learning being applied to the side channel analysis problem, and that's being very effective, and it creates a kind of opportunity for there to be script kiddie tools that will run a power analysis attack for you. That's a very scary prospect, because as soon as that happens, you've got open source software kits being downloaded from the internet. Every physical device that somebody can get access to, which is a lot of inexpensive consumer-oriented devices that have cryptographic keys in them. Think of things like gaming machines and all kinds of other stuff. Those things become targets for side channel analysis attacks being done by people who have very little skills in this area, but they know how to download software and run it. And we're at the cusp of that becoming a real threat very widely through the industry. So I think that's one of the things that's going to change everything when those tools actually become available and we start seeing them in the wild a lot. Then a lot of things start to be targets.
So you're not helping with my sleep patterns?
No,
Doesn't sound like it.
That's kind of my job.
Prabhat, talk to us a little bit about your perspective on the research side. What are you observing out there? What do we need to worry about going forward?
So from a research perspective, I want to take a different view. So it may be difficult for you unless you actually hacked a device. Think of human body as an electronic device. The time you grew up, your parents are telling you, do this, don't do that. You might have hated it. But now when you keep your glass on the side of the table, you are still remembering, my mom said not to keep it, it's going to fall down. That's a side channel attack. So what your parents did, and politicians and religious gurus perfected, they actually know how to manipulate you and play with your emotions. So here, the example Mike took or Will took. So side channel doesn't need to be the key. They don't need your ATM card and PIN. They may be able to extract more money by making you believe things and then extract in long run. If you think of a state actor, they might not be attacking your tiny smart card. They might be attacking your router system. And the attack example, we are taking power and timing. That breadth is huge. And then you combine with that your socio-economic beliefs, and all of that once you combine, then attack surface is huge. So on the research side, people are looking at it from different dimensions. So for example, people in the architecture community are looking at the Spectre meltdown, the discussion you heard. How, when some computation is happening at the software layer, what kind of thing you can do? When you go to the physical side, there are many ways. One example you heard that if you are doing a laser fault injection attack, you will be able to extract the key. Think about it. Laser fault injection, depending on the capability and precision, if you have a finite state machine where you get password, check password, and get the money. So if you think of an encoding, the get password is state 0001 and get money is 10. So if you are in state 00, all you need to do flip one of the bit. Then you actually got the privilege level of 10. So you are actually in withdraw money stage just by flipping a bit. You might be thinking, wait a minute, I'm thinking of a state machine, one box, one arrow goes there. But the way it's implemented as a flip-flop with 2 bits. And depending on what the flip-flop value is, that's the functionality it's going to do. So if you change 00 to 10, done. You don't need to password check, you don't need anything, you got the privilege level. You can become a king for a day or king for life. So the scope of side channel attack from the research perspective is huge. I'm the only odd one here from academia. Everybody else is going to give you practical perspective. What's happening today? I can tell you, anything can be hacked. The device inside your body, whether you're a pacemaker, there is a lot of research to say that. Human mind, electronic devices, anything can be hacked by looking at, if I'm walking next to you and your breath smells, it's not necessarily you didn't brush properly. I can tell you what kind of medical problems you have. I can start selling you medical products. All these social network side you are using, they're also side channel attack. And you are probably not feeling it, your kids are feeling it. From the childhood, they got hooked into it, and their mind got tuned, and we call it a teenager syndrome. It's nothing, it's a side channel attack. That's pretty much I have.
Good stuff. Before I go to Tomcat, because he's going to upset the apple cart in a very entertaining way, are we doing enough in the tools and IP side of the equation right now? Is there a little bit more to do or a lot more to do?
So I'll take this one, and I think that from my perspective, there is a huge amount of work to do. There's absolutely huge amount. My background prior to working with FortifyIQ was, and some of you may know me from on the power side, I always used to say and still say that power is an equal opportunity problem. Everybody can contribute to the solution. It exists all the way through the flow from system level down to sign off. And I kind of look at security in exactly the same way. It is also an equal opportunity problem. It takes an ecosystem, it takes partnerships, it takes tools at various levels of abstraction, it takes verification AP, it takes sign off, it takes protected design AP as well. So there is a plethora of things that are needed to be done in the security area. That's my perspective on this.
I mean, I think one of the things we've seen a lot of is that there are a lot of ad hoc tools and ad hoc approaches to solving this problem. And it's time to bring a little bit of systematic thinking into the process of building things that are immune to side channels or that try to mitigate their side channels. Part of that systematic thinking can be, you know, I've got other devices around in the same chip with me. What can I do with those to obfuscate this power signal? How can I use those in a way that prevents that power signal from being, you know, just pulled out very quickly using a side channel attack? Through the design flow, there's a lot of things in a top-down sense that you can do to mitigate the side channels. And, you know, oddly enough, side channel leakage is something that can be introduced through a lot of parts of the design process. So the first thing is to try to design the IP, things like the cryptographic cores, things like the instruction sets for the processors, in such a way that they are very consistent, very regular in their power usage, regardless of what states are present in the entity. So there are some, you know, top-level design things that we can do to improve the situation and to mitigate side channels right away at RTL. But then you go to the next level. As soon as you get to gate level, there's been a round of processing applied to the RTL, and that has created an interpretation of that RTL that is closer to a physical realization. Subsequently, you're going to add more and more components to that flow and more tools in that flow. And if you're not careful, all of the careful work you did to mitigate the side channels at RTL level becomes a new side channel that's introduced after gate level. And so we need to see, you know, more consistent flow through the tools, a way to identify the things that are important. And there's work that has started to take place to do that identification of what the security assets are. You know, cryptographic keys are one security asset, but the plain text is also another security asset. I don't need the keys if I can get the plain text easily. So, you know, those kinds of things, that kind of thinking needs to go into the process of developing these. And this is a very fertile place, I think, for CAD tool providers, for new thinking, for university research, and for the tools that will come out of that. You know, companies like ours will be interested to incorporate those as markets come on that want to consume them. But fundamentally, we depend on, you know, very good research coming out of places like University of Florida and Prabhat's team and his colleagues to develop these things.
So it's obviously a...
If I may add, so when we talk about IP level, first question you as a designer or manager want to ask, do you care if what you are computing anybody knows about it or anybody able to manipulate it? If you don't care, then it's fine. But security asset we always talk about. Even if it's not security asset, if I'm able to figure out what you are computing, why are you computing, I might be able to do the attack. My students takes few minutes to attack a car, not because a car doesn't have the electronic control unit is not secured. It is, but infotainment portion is not secured. So you get foothold there, a stepping stone, then from there you do the attack. It's much easier than you directly want to attack the well-protected electronic ECU unit in your car. So when you write your RTL code, and if you have some kind of side channel vulnerability, what Mike was talking about, if you have a if statement, unbalanced if statement we call it, the if part is large, else part is small, or else part not there, that's where the attacker would be able to figure out what's happening. So you need a set of tools that would be when you are designing, if you believe you don't want to have a side channel footprint, you want to analyze and you get a score. I call it a Borza score. You want to get a score, how good that is. And then you do your mitigation, run that, and that metric is important. Now RTL may be good, now you synthesize a lot more artifacts get added, and maybe all the stuff you have done, many of it is gone. So you might have to do it again, and you have to do it for all the side channel vulnerabilities, and it's going to cost you. So you have to believe this is important, and you should be willing to spend for it. It's going to cost you in terms of area, power, and whatnot to do some of these mitigations, and more research is of course going on so that we can give you a close to free solution where you get what you want but you don't pay too much.
So in the arc of security history, I think we've gone from the era of solve your problem and throw it over the wall to the next guy to much broader industry awareness of the massiveness of the problem. Tom, talk a little bit about your perspective on this, and who are we actually trying to help here?
Before I do that, I'd like to, can you hear me? Okay. I'd like to address some of the points I made. I bought my first earthquake kit in the late 80s, after the earthquake occurred. So the question is, you brought it very correctly, is who cares about this and why we should care about this? Obviously, there's a lot of scary stories about people compromising your keys, taking your keys, and eventually compromising a fleet of devices, which can affect safety, et cetera, et cetera. But in our industry, EDA and chip, we're far away from those events. So the question is, how do we really get those people to see the importance of, if the chip's power profile is compromised and the keys are stolen at the end device, what does it mean? And there's two items that are very important, the fear factor and the value factor. The fear factor, which we always say in security, is what's going to happen to you, all right, if that is compromised. But the value factor is much more important, I think, because if we're talking about billions of devices that will be powered by trillions of chips, all right, those devices will produce data, and everybody wants to monetize the data. The era of the hardware is over. Everybody, whether this is chip suppliers or ODMs or OEMs, care about, I sold the razor, but now we're in a connected value chain, and there will be data coming out of those devices, whether they're chips or PCBs or systems or the edge. There will be data coming out that needs to be used to be brought back for digital twins, that needs to be used to be monetized, to do services, et cetera. So if my keys are compromised, is much more than the safety and liability that can occur. It's also the fact that I'm losing the ability to monetize, because the compromising of keys, the ability to take the keys out of my device, means that they're able to get the data of my device, which data that I want to monetize. So the first thing is, why should we care about side channel attacks? It's something that happens at the end application. We show the slide where a PC sits here and Arduino sits over there, and within 2 hours, with a very low computing device, you get the keys out. What happens if I have a much better device? And what happens if I do that to a high volume system? All right? Not only compromise the system, but I can compromise the data that comes out of the system, and therefore the ability to monetize. So if we look at the operating impact of doing that, on the one hand, you have the risk, the liability, the insurance, all these things that happen. But on the other hand, you have the value that you would not realize. So the problem, though, is, going back to why it's not adopted, okay? And I will get back to GSA ties, is because the chip guys are too far away from that problem. So the industry by itself has to educate and has to basically get closer to the end application to understand how they're going to bridge the gap between end-to-end solution. We try to do the same thing from a chip point of view. It didn't work. That's why we created the Global Semiconductor Alliance Trusted IoT Ecosystem, whose basically mission is to get the end application guys to tell us the problem so we can get an end-to-end solution. And that end-to-end solution may start from very much from the verification, from the analysis, the power analysis that we do in the 88 flow on chips, that can go down to a VIP, that we can actually verify that together with the stimuli at the end. They can go to FPGA, they can go to a kit of a chip, they can go all the way to the edge. Because if you cannot do that, then people will not recognize the value of penetration.
So fundamentally, though, Tom, there's a disconnect here, which is that the chip is the best place to put the security.
Correct.
Put it into the chip, burn it in, so that it's there, it's present, it's ready to be used. The difficulty is that the chip vendor sells that to a system designer, and that system designer is going to build it into something that's used in somebody's service down the road. And the person who gets the benefit of that is the users of that service, ultimately in the field. And so that service has a vested interest in trying to maintain the security of their service, and not to be perceived to be, lax on security and a gateway into, people's homes and hearts. But the problem is monetizing that.
Correct.
In a way that makes sense for the chip vendor.
Correct.
If the chip vendor has to do all this for free, the only lever that's there is that they can't sell their chip if the security isn't present. And we're not at the point where, people will not just end run that by buying an insecure chip if it's 20 cents or $2 or, 1 cent cheaper. And that's the juxtaposition that we have, is that the thing that needs to be secure isn't secure because it adds some cost, and that cost makes the thing uncompetitive when you've got people trying to deploy these widely.
However, we have in GSA ties, Azure and AWS, that they come in not because they want to monetize security on their own chips, but because they realize that whoever controls the root of trust and the monetization of that will also control the path to monetization of data. Right?
Correct.
So this is very important, and that's why this business of root of trust and side channel analysis, they come together into a package, into a chip that needs to be connected to the outside world and the infrastructure that essentially ultimately creates monetization. The monetization problem is tough because everybody's thinking that if I put security, there's a way to monetize, but how do I control that monetization? The answer is you don't unless you digitalize the supply chain. In other words, you create a digital thread in a way that design or manufacturing, you track everything that is done, and if there is data, for example, that was produced as part of testing or simulation or whatever, to a single entity, that data can be digitalized, encrypted, and become available to the downstream. All right? So that now connects the physical asset of chip security and design with the digital asset of the enterprises and the whole procurement departments.
There still needs to be a way to share that pie amongst the players.
That pie can be shared only through indexing, metadata, blockchain, where the indices point to the internal enterprise data that can become available on a per license basis to the guys downstream that need it. And by the time you get the device, there will be the device supplier that gets some data, but his data will be a derivative of all the data in the value chain, and therefore everybody's participating, and that's the key. If you don't make this an ecosystem business motivation, this is not going to work out.
Right.
So I'd like to add to what Tom was saying in terms of the two sort of sides of the coin, the risk factor and the value factor, right? So because what we're seeing also, and I'm sure you guys are seeing the same thing, is that we're now, our customers at least are getting regulatory requirements coming in as well. So that to me really speaks more to the value. It's not really a risk, but it's the value where if I can meet those requirements, I can differentiate my product from somebody else's who doesn't meet those requirements. They may not even get a design win. It's not even a competition at that point. And the other part of it, of course, is the early bird gets the worm. So if you have the device that meets those requirements early enough, you'll be able to get the design win. So our customers are beginning to think about how do they get ahead of the curve? How do they meet those requirements early on? For example, how do they design IP that is protected against side channel attacks such that that IP can then be leveraged in future designs as well? So I think that the regulatory aspect of this really brings a lot of value to the value portion of this.
Correct. And regulation is what's going to force the chip suppliers to say, I got to have it in my chip. Yeah. Because I realize it will be a differentiating component since the regulatory agency is going to promote that.
Or it could be just, without it, I can't even play. That's
correct, exactly.
Simple as that.
And that's why it links to the data, because the chips will produce data. There will be security, there will be sensors inside the chip. There's a lot of movement right now we see in the Global Semiconductor Alliance. Those sensors will have to get the data out security, and that means there's got to be a key. You're going to have your root of trust in there as well, but you're going to have your keychains. If any of that is compromised, all right, then the whole industry goes down. So it's not just, it's not just Internet of devices. It's also Internet of chips. Let's be very clear about that. When you have a chip in an automotive, in a traffic, inside you're going to have 150 ARM cores in there, and your threshold of failing is at 100 ARM cores, and you have 5 nanometers, and suddenly this start failing. If you don't have the ability to securely transmit data that can get to the potential functional failure, you're dead. So
it's the weakest link that breaks the whole thing.
Correct.
Right.
So really, it's not just the scare about it. It's also the value, because once you get the data out of the chip, you can do a lot of things. You can do silicon lifecycle management. You can do all kinds of things. But all of that has to come together: the root of trust, the key chains, and of course the DPI analysis, where you can develop the trust in the chip design, but you can develop mechanisms to verify at the end application. That's the end-to-end trust of verify.
You guys are doing a fantastic job of raising my anxiety level. So thanks. Anybody in the audience have questions for our panelists? I have plenty of more, but please identify yourself, Mr. Covey.
Okay. Lou Covey with Cyber Protection Magazine. How do I set this up? Basically, when you're talking outside of state actors, you're talking about people who are looking to make money as quickly as they can, as easily as they can. And when you're talking about hacking a system at the chip level, that requires a lot of work and a lot of training and a lot of equipment in order to just get into the chip. But still, it doesn't guarantee them any kind of payday at the end. It does guarantee a payday for a research company who is trying to show that a particular chip has a hole in it, because they will get paid to help that chip company close it down. So going back to one of the questions that Brian had was, what does that mean for people who are just using a cell phone? I mean, is it that important to us at that point, or is it more important to a chip company just to, as you say, if it goes into regulation, we got to put it in, so we got to budget it in? So
given the amount of stuff that most people carry around on their cell phone that is very private to them, I think they should be very concerned. I don't want somebody having access to the credit cards that are in my phone. I don't want them having access to the password vault that's in my phone. That gives them access to things like my bank accounts, like my other compute systems, all those kinds of things. So that concerns me. It concerns a fair number of people. There are other people who blithely go about their lives assuming that they'll be okay. And so far the evidence is that many of them are okay. And then you get a few people with real stories of woe after they've lost a whole bunch of stuff that they really cared about, like the contents of their bank account.
Yeah, well, I understand that, and I completely agree.
Can I just add to that? Yeah. So I don't have as much money as Mike, so it's fine. But still, I open my front door with my cell phone. I lock my alarm system with cell phone. So I know you are talking about cell phone, and maybe someday cell phone would be in the critical or control list, but it's really the weakest link. If your thermostat, and University of Florida broke the first Nest thermostat. So if I break your thermostat, I got control of your house. Mm-hmm. I know what you are doing there. Now, if you don't care, it's fine. Why do I want to know what you are doing? That's a different story. All I'm saying is, in the software layer or on the important devices, only so much you can do. If there is a vulnerability, I might be wearing all this dress, but if internally I have low ethical value, it would be easier for you to attack me at some point.
But I'm not going to go spend 2 hours to hack your home. I want to go spend 2 days, 2 weeks to hack up millions of devices as part of the fleet management system. Yeah. That's what I care about.
So that's part of the point.
That's the point. Point is, because we are not designing diverse systems, in here I'm seeing only so many female, only few females. So diversity, if you don't take into account, I break one light bulb, smart bulb, I broke all of them. I broke your phone, meaning I broke pretty much everybody's phone.
In order to break all the smart,
that is the key. Is that, a lot of those hardware attacks that you're talking about.
If they're all different, then your argument holds. If
in
order to break, but I'm breaking all of them.
But a state attack needs to break the light bulb, and then needs to get the database of all the light bulbs and serial numbers and be able to attack those from a very different angle, all right? So that's what we're going with. We're not going about a single hacker that can do this, but we're talking about the billions of chips to the trillions of devices, and the infrastructure goes on top of them.
Yeah.
So those will become very sophisticated operations of breaking for either monetizable benefit or for espionage. And espionage is different than cyber attack. Cyber attack is one thing, espionage is another, right? So those are sophisticated operations that you go down to the chip. I mean, the demos that you go see on the internet, you see some Israeli guys that have done some phenomenal jobs at the time of side channel attacks. And they just put in a sandwich or in a pita bread, put a little Arduino in there, and you put it next to your PC or whatever, and he goes all your keys, right?
Yeah, well, let me give you an example, because I don't disagree with anything you're saying. But I was tracking the activity of a Pakistani hacker group that was putting up posts on Facebook about dogs. And I found, including my wife, gave up all kinds of personal information. I mean, it was just basic social engineering. It was so easy to do. And it had nothing to do with hacking the hardware. It just had people giving up their information that could allow them to hack their devices.
Sure, but that's been true for a long time. Inherent in your question, though, was a statement that it takes a lot of expensive hardware to do these kinds of attacks. And actually, I would tell you that the cost of that hardware is coming down all the time. So it used to take a lab with $1 million of equipment. Then it takes a lab that's got $100,000 worth of equipment, and from there it's somebody in their basement with $10,000 worth of equipment. At the start of the pandemic, equipment selling on eBay, or actually coming out of the last recession, equipment selling on eBay, $100,000 instruments were going for $1,000 on eBay. And so you could set up a lab, very capable.
You can get a lot of software-defined
ton
test
of
equipment.
software-defined attacks.
There's even at the risk of pitching a product that I've heard that I thought it was a really cool name. There's something there called horoscope.
Yeah.
Horoscope, really with an R, not horoscope. But I would say, from my perspective, at a personal level, this is what I see. You don't care until you care, right? That's, if business as usual.
No,
for
you have
and
to be
your device,
proactive. We're not solving the technical problem.
No, I'm talking from a personal.
But we have to look at the strategy. If you want to be in IoT, and you're going to have connected devices, you got to do design up front, secure by design up front, right? You're looking 3 or 4 or 5 years away in IoT devices that will be connected. If you don't account for this now, what are you going to do in your next level of chip?
I agree.
So
we're not at the point, though, Tom, where a lot of companies are taking that approach. Some of them are. The most foresighted ones are. The people who are going to operate big ecosystems, you said Microsoft and Google, they have a big ecosystem already, and
that is
Amazon,
why,
of course, they're starting to take this very much more seriously than they did.
Yes, but that's why we're taking it to the Global Semiconductor Alliance.
Oh yeah.
We want to educate
so
everybody.
I don't disagree with that.
We want to promote with everybody.
Right.
And we want to accelerate that.
But what I'm saying is that there are still a lot of fly-by-night companies or small companies that are basically, they're in a foot race, and they're running as fast as they can to try and create as much value as they can as quickly as possible. Right. Hopefully get bought by somebody before they have a big incident, and then it becomes somebody else's problem. And that's what we saw with Nest. Google bought Nest and happened to be running ahead of when you could hack a Nest device easily.
We're back to the risk part of the equation here.
Exactly.
Any more questions?
Anybody else?
We have time for about one more question if we have any. Going once, going twice. I'll ask the last one.
So I'll respectfully disagree with your comment. Emotion is a side channel value. I'm a researcher, and social aspect of it, I know all of you are talking about electronics. Human brain, human body is an IoT device. When you talk about connected devices, human body is a connected device with all the documents. And that's the most important device you can hack. And emotion is a key part of it. To get data from your house, if only blackmailing you with your dog or animal lab capability, that's good enough, done. If not, I might have to do a complex attack, brute force attack, all that stuff. So emotion is a side channel signature from all researcher perspective. And in research community, we learn from biological community, biologically inspired computing. Many of the security attack and mitigation going on in research community are by learning how these religious gurus manipulate brain, how all these fake counselors talk about psychotherapy and all that nonsense. We actually learn from it and we apply it to electronics, and then we get published paper and people like Mike gives a lot of money. It's a good ecosystem.
But the problem still remains. You got to get this to the masses. The adoption right now is very little, and part of it, I think, it depends on the adoption of root of trust and key chain from the chip, because those are all related. But that's exactly what needs to happen. We need to basically raise the awareness. In order to raise the awareness, there's two levels. One is the awareness to the chip suppliers in what happens in the end application, but more importantly, the awareness from the end application, what they need to have in the chips in order to be able to prevent that from
Create a
happening.
pull, not a push.
That's where the requirements are coming in from, right? Absolutely.
Yeah.
All right. Well, with that, I'm going to make that the last word. Let's give a round of applause to our panel of experts. And I'm sure some or all of you might be up for a minute or two to chat with people if they come up. So thank you very much.
Thank you, Brian.
Thanks all.